So, welcome again. So, this is the introductory lecture 2. In the previous lectures, we talked little bit about the Earth's atmosphere, how it was formed, what are the important components of this one, and then how the oxygen came into our atmosphere. In this lecture, now we are going to discuss the uniqueness of the Earth's atmosphere. So, in what sense the Earth's atmosphere is very different compared to the other ones. So, this is really very interesting lecture and which needs little bit of the mathematics, not very big actually, just a simple equations and calculations. So, I am sure that you must practice this one and you will be able to learn this. So yeah. So, why do we say, when I say that what is the unique? Earth is a very unique and habitable planet. When I say this one, what do I mean by unique and habitable? So, first of the things, in the last lecture we discussed its habitable environment, that why the Earth is habitable, okay. So, that we have already discussed. But now the question is that how these location composition is actually made this Earth as a unique and habitable planet. So, if you look at this, actually Earth's location, Earth's position in the solar system. So, Earth is actually situated just 1 astronomical unit distance from the Sun. 1 astronomical unit AU is actually 1.5 into 10 to the power 8 kilometers. So, this of course, this one AU is defined itself that the distance from the Earth to Sun is actually 1 AU, but the point is that why the distance is 1.5 into 10 to the power 8. What would have happened if the Earth was located say 1.5 into 10 to the power 7 kilometers away or 1.5 into 10 to the power 9 kilometer away. So, this is why only 1.5 into 10 to the power 8. This is really very important for us to understand. Then if you look at the global average temperature, so the Earth's global average temperature is about 15 degrees centigrade, right. So, that 15 degree centigrade temperature, it's and our body can actually accept the temperature say around say close to very 0 or little bit up to say 30, 35, 40 degrees centigrade. And the global average temperature is such a beautifully planned that our body can actually adjust accordingly. So, not only our body, all the living organisms, they can actually adopt. Of course, now we have lots of discussion about the climate change, and then lots of species are getting diminished, actually they are actually not there in that in the system because of the temperature is rising, or lower temperature of course is not there in some regions, but because of the rising in the temperature some of the things are shifting or some of the things are lost. So, that's a different topic altogether, but we must know that why the temperature is actually, and I will just show you next couple of slides that this distance was very important to make the Earth's temperature as 15 degrees centigrade. The third point is very important, the presence of the atmosphere, its composition and amount. Now, as I said that in the very beginning, I said that atmosphere is important, but at the same time I said that not only the atmosphere has to be there, its composition and amount has to be in the perfect amount, in a perfectly actually. So, if the composition is for example, if some species are present in the high concentration, some are in the lower, then the atmosphere can also not be survivable, okay. For example, you look at the Mars atmosphere, or you look at the actually Venus and others. So, the atmosphere is there actually, but the point is that the atmosphere is such a way, it is dominated by few species which cannot make the atmosphere sustainable or habitable. So, in our atmosphere we have majorly nitrogen, oxygen and argon. These are the major gases and they occupy about say 99.5% or more than that, and then we have little bit trace gases CO2, CH4 and ozone, and many other gases are there actually. So, lots of list is going on in this one. So, you can have those things. Now, here another very important, major gases are important actually. So, they are overall, they actually somehow sort of has to be there, but the importance of trace gases, especially these global warming agents species, carbon dioxide and methane, which we call is actually greenhouse gases, and ozone of course, N2O, they are really very important. We will see that one, we will come back to it, this one. Then of course, if you look at the water and soil for the food, this is already there actually, because for surviving you need food, and for food you need plants to do photosynthesis if you are a vegetarian. And if you are not a vegetarian, then it was actually like, we had a life which was actually kind of dominated. We call it, our ancestors were eating whatever they had actually. Now the point is that you can have soil, you have water, so you can cook your food, or plants can make food for you, and that you can eat actually. For that actually you need carbon dioxide, sunlight and carbon dioxide. For the photosynthesis, that is already there, because we have sun's temperature or sun's radiation is already there, and in the atmosphere you have carbon dioxide. Okay. Then there is a very important topic, that is aerosols, and many more things are there in the atmosphere, and this is my favorite topic, of course, because I work on the aerosols. So I can talk lots about the aerosols in this one, and I will discuss more of aerosols and air pollution. I will be discussing more both gaseous air pollution as well as aerosol particulate matter pollution. So we will discuss this one. So these are the few very things. Now let's come and see this one. Not only that, another very important features, and I must tell that if you look at the importance of the different layers of the atmosphere, you all have seen this atmosphere. It starts from troposphere, then you have tropopause, you have a stratosphere, mesosphere, then you have thermosphere and ionosphere. Okay? And if you look at the temperature profile, it's kind of zigzag, moving, going back, and then increasing, decreasing, increasing, decreasing, sometimes keeping it constant. Now this is actually very important, and if you see the presence of the ozone in the stratosphere, you can see that is somewhere around 20 to 25 kilometers. The ozone is highly concentrated, and this is again very important. Now you can imagine a situation that why the ozone has to be there between 25 or 30 kilometers. It could have been up or it could have been lower. Of course, we have in the lower, we have another ozone that we call it actually tropospheric ozone, but tropospheric, apart from the tropospheric ozone, this ozone is present, and that is present is a very specific location, a specific altitude. Why? This is also very important, and this is actually, I will come back to you and correlate that this is very important for the control of the temperature. Now you see here, so if I just correlate this one, but the major composition that we have actually. So if you start from the heterosphere, from the top of the atmosphere, you have air flow in a almost like a laminar flow. So because there is no friction there, air is flowing like whatever way it is, very perfectly. Then in the below you have helium, and then the heterosphere you have atoms like oxygen, nitrogen and oxygen. They are actually there, and here only ions are formed actually, and because these are ions are only found in the ionosphere. Why not on the top? Because you need, for the ions to be formed, you need some species ions are formed actually. So the energy has to be exactly same or corresponding to the strength, bond strength of the species. If the energy is too high, the bond will break and nothing will remain. But if the energy is too low, and if the energy is too low, these bonds cannot be broken, and if the bonds cannot be broken, you cannot form ions. So ionosphere, we will see that what is the importance of ionosphere. This is a separate field of studies, lots of people working on this one. Okay. Then you have a turbopause, and then between turbopause and homosphere you have a very turbulent mixing, lots of mixing going on, somewhere around say between 40 to 60 kilometers or 80 kilometers or so, lots of turbulent mixing happens. So we really, what we feel that atmosphere is very beautiful. We don't know that what is happening in the atmosphere say above 40-50 kilometers. This is very important. And then somewhere around below 40 years you have homosphere, and here homosphere you have actually composition that is fixed, nitrogen, oxygen and argon. So the composition is relatively constant here. Now this is actually, now I am trying to put things together in a perspective so that you can understand and appreciate the importance of these things. We know that sun is actually emitting radiation as about 6000 Kelvin. 6000 Kelvin, note the temperature that Earth's surface is emitting. And we also know that the radiation from the Earth's sun's surface, it travels as a electromagnetic radiation, and the energy decreases as a function of 1 upon d square, 1 upon distance square. So, if you are closer to the sun, you will be receiving more of radiation. If you are away from the sun, you will be receiving less radiation. Okay, and that is why I said, and we will come back to this, that Earth is actually located a very specific, very precisely at a place where the temperature, where the substantive amount of what you call radiation is there. Okay, and of course, the sun emits in all the wavelengths from high to low energy. Now, imagine these, actually I said that the atmosphere, the different layers of the atmosphere, they actually acts like a filter. So, like we have in the houses, our houses, we have actually what you call, actually everybody nowadays uses this water filter or water purification system. So, different levels are there. First you separate if there is a something sand or not, then you have go to ozone, you put this one. Okay, so you want to kill all the actually bacteria and other things, and then finally you have a TDS, you want to remove the TDS. Okay, so you remove the TDS, and then finally you want to have whatever kind of water or whatever quality of water you want. Now, the same thing happens here. So, Earth is, sun is giving radiation about 6000 Kelvin, it is getting filtered. So, if it is not filtered, the energy is not filtered, all the high energy radiation would have come to the Earth's surface. And if all the high energy radiation could have come to the Earth's surface, can you imagine that the Earth's surface would have been say around 6000 Kelvin? So, can we survive here? Obviously not. Now, here is the important, that these energy are filtered by different levels, at different levels by different type of atoms, molecule and particles. This is precisely very important. So, again I give the I say that appreciate the nature or creativity and its creativity, or the creator itself. So, who is the creator we do not know, but we must appreciate. And finally, when the radiation reaches at the Earth's surface as electromagnetic radiation, it still contains all the wavelengths from high to low, but some of them are actually very high energy. Radiation has already is absorbed in the upper atmosphere. So, they are very harmful. So, they are actually already absorbed, and by the time it reaches Earth's surface, the temperature becomes about 288 Kelvin. Now, imagine, this is very important, that our Earth's temperature is 288 Kelvin, means about 15 degrees centigrade. This is global average temperature. This is precisely, so it is not, you are having a source which is giving energy at 6000 Kelvin, and you on the way it is making so much of the filtration of the high energy, that we are fortunate enough to get only the radiation that is actually giving 288, or the radiation that is coming on the Earth's surface, we are only keeping it making the balance. So, all the level of the atmosphere here and then species, they are very important for us. Okay, I talked about this actually, like presence of ozone in this one. You can imagine this one. Ozone actually absorbs lots of ultraviolet radiations. So, if we will discuss this probably in the next few lectures, that why ozone is very important. And this is how it happens. The habitable environment, when I say, so the globe, but again a very important thing is here. So, as I said, and I have been talking about, that global average temperature is about 15 degrees centigrade. But what would have been temperature if you predict this one by equilibrium model? So, I think I should have some board and other things to explain this one. We will try to do in the next lecture or so. Now what is important here, that what governs. So, this means what is happening here? Global average temperature is actually 15 degrees centigrade, which is measured or observed, that one. But if you just predict by the equilibrium model or steady state energy model, the temperature would have been minus 19 degrees centigrade. So, there is actually like minus 20 here and 15. So, there is a difference of about 35 degrees centigrade between observed and predicted temperature. So, 35 degrees centigrade temperature difference is already there, and how it can be, we need to discuss this one. Okay. So, this is what picture is shown here. The same equation is explained in the next lecture, so in the next slide. So, this is how, what controls effective temperature of a planet. So, and if this equation I will derive in the next few lectures, just keep this equation in mind, that T effective is 1 minus alpha into S0 upon 4 sigma, and you take fourth root of whatever the number comes out to be. Now, here in this equation you have T effective is effective temperature, means you assume that there is no atmosphere, okay? Because this is what you have to do in the radiative balance equation. You assume that there is no atmosphere and then calculate the temperature. Alpha is albedo and S0 is solar constant, that the radiation that is emitted from the sun, and what is the radiation that is reaching. So, radiation that is reaching on the earth's surface or earth's atmosphere is called solar constant. So, we need to know, and then 4 sigma. So, sigma is actually Stephen Boltzmann constant. So, we know that this is actually constant. So, it does not have many, it cannot do much actually here. So, if you see this equation, there are only 2 variables. Can you see that? Whose are 2 variables? Alpha and S0. Either albedo can vary or the solar constant can vary. Now, see that name actually, the name says solar constant. So, this means this S0 is also constant. Yes, it is actually constant in a larger context if you compare the numbers, but if you talk in a year scale and then finer time scales, this is not constant. There is a slight variation about 0.1% or so. So, I just said that there are only 2 equations or 2 variables that can control the effective temperature. So, albedo and S0. So, if the albedo increases, what will happen? 1 minus alpha. Okay. So, 1 minus alpha will decrease, it will be lower, and keeping S0 constant, the effective temperature will be lower. And this is what is happening, people talking about increasing the albedo of the earth's surface or the earth's atmosphere. So, if somehow or other we can increase the albedo of the earth's atmosphere, much of the radiation will be reflected back, much of the radiation will be reflected back, so the earth will become cooler. There are tools to do that one, but it is actually not feasible so far. So, we have to still wait for this one. And then S0 is actually constant, as I said that one, but this is actually like so you can see this one. Now, one more important thing is here. So, if you see here, I gave the equation to you, just keep this equation in mind, and you can write down this equation, that how it is calculating. So, this is you just give. So, now if I ask you again that what controls planet's climate on the planet, climate here I mean for the sake of complexity, let us say that climate is actually temperature, the measurement of climate is actually sun's atmospheric temperature. Okay. So, if you talk about so this means what controls climate on the planet means what controls temperature of the atmosphere of the earth or any other planet. So, what are the things? The input energy, basically the energy that is coming from the sun or radiation, and then other things like albedo, I just said that albedo. Okay. So, energy from the sun is there actually, and then albedo. Now, consider these 4 planets. You have sun, then the closest to sun is actually Mercury, Venus, Earth and Mars. You just see these 4 inner planets that we have actually, and if you see their distances, Mercury is about 0.4 astronomical unit, Venus is actually 0.72, Earth is at 1 astronomical unit and Mars is about 1.5. Earth actually receives about 1670 watts per meter square of solar radiation. 1670 it varies actually, sometimes you will find 1672, 1673 or even 1665, but just remember this number 1670 for the sake of calculations, we will do this one. So, if you see this one, the earth is receiving 1670 watt per meter square solar radiation. In contrast, and we know that the energy varies 1 upon d square. So, this means that Mars would have been receiving less energy or radiation compared to the Mercury and Venus, and this is what is actually there. So, Mercury is receiving about 2250 watts per meter square and Venus is only 660 watts per meter square. Now, remember this one actually there is actually a term missing here, you have to multiply these numbers by 10 by 4, because when the calculation, final calculation comes 1 upon 4 sigma. So, S0 is actually either you take S0 as 1670, or if you do not take 4 sigma, or if you take 4 sigma, then you have to take this one, you have to multiply this by 4. So, 660 into 4 will be the number, and 2250 into 4 will be the number. In contrast to Mars will be receiving only 150 watts per meter square or 600 watts per meter square, if you just take into 4 times. So, this means you can see very clearly that Mercury is receiving more energy, Venus is receiving more energy compared to Earth, but less than the Mercury. Mars is receiving the least energy. There is actually little bit confusion. So, I will redraw this graph again, or we will discuss in the next lecture. Just remember that the Earth's the Earth's radiation received is 1670. It actually has not to be multiplied by 4. The other has to be multiplied by 4. So, just remember this one. Okay. So, if you just rearrange that this equation, the previous equation, T effective 1 minus alpha into S0, and if you see here S0, you can see that S0 is actually for Mercury is 2250, Venus is 660, and Earth is actually 342 because 1670 divided by 4. So, it will be around 341.5 or 342, and then Mars will be 150 watts per meter square. Okay. And the relative distance is given. So, in the equation you do not have distance, but you have albedo alpha. So, alpha is actually, what is alpha? If you see in the column, albedo is actually Mercury albedo is about 0.59, Venus albedo is about Mercury albedo is about 0.1, albedo of Venus is about 0.59, Earth's albedo is about 0.3, 0.31, and Mars is actually 0.15. So, if you see the equation and calculate the temperature by arranging these numbers, you can calculate that the actual temperature or equilibrium temperature that can be calculated by this number will be for the Mercury will be 162 Kelvin, for Venus it will be minus 10 degrees centigrade, for Earth it will be minus 19 degrees centigrade, and for Mars it will be minus 55. So, what is actually problem here? You see and then actual temperature of these planets has been observed. Mercury has about 162, and this is actually equilibrium predicted, and then measured temperature is about 180 watts Celsius. So, this means they are little bit agreeing, actually not very much far difference is there. But if you see minus Venus, equilibrium says that minus 10, but actual temperature is 453. So, there is huge difference in this one. So, this disagrees badly. For the Earth also, the equilibrium temperature minus 19 and actual temperature 15. So, this is also varying a lot, and this is actually also disagree. But in the Mars, if you see, minus 55 is equilibrium temperature and minus 43 is actually calculated. So, these two agree. So, even in the 4 inner planet system, the temperature that is predicted by equilibrium model and actual temperature that is measured is almost like matching for the Mercury and Mars, but they are not matching for the Venus and Earth. So, now what is the problem? Why there could be a reason? So, we will come back to again here and we will see this. Okay. This, apart from this, there something else is playing a role. Apart from S0 and alpha, something else is playing a role, and that is actually called composition of the atmosphere. And as I said in the previous slides, that the Earth composition is actually like nitrogen, mainly dominated by nitrogen, oxygen and argon. These are the major gases, and just 0.1% or so, or 0.5% less than that, you have other gases, minor or trace gases, carbon dioxide, carbon monoxide, methane, hydrocarbon, ozones, all those things here. You can just see the below picture. I am sorry, this pointer is also not working, and this, so it is very difficult to navigate, but it is okay. So, okay, let us go. So let us go and see what is happening. So, this composition, and this is the reason carbon monoxide is actually making it very important. So, the temperature difference is because of the importance of the greenhouse gases in the atmosphere. Carbon dioxide is a greenhouse gas. It traps the outgoing thermal radiation and leads to the increase in the atmospheric temperature. So, as I said that in this one, Earth actually minus 19 equilibrium predicted, but 15 is actually from the actual temperature. So, here the carbon dioxide role becomes very important. So, what will happen if you, but the next question is that what will happen if you keep increasing carbon dioxide concentration. This is very important. So, if you keep on increasing carbon dioxide concentration, the radiation that is trapped within the atmosphere will keep on increasing. So, the radiation in the trapped atmosphere will increase, means the temperature will increase, and that is why we call it, actually we learn about the global warming. We see these things, that global warming is a very big threat to us. It is again described here. So, in a condition you have actually like you have terrestrial radiation that is coming, and you have Earth's surface shown in green. So, it actually what it does, there is a balance between the incoming and outgoing radiation in the terrestrial radiation. Okay. But when we are extracting more of the fuel, or we burn more of the fossil fuel, we are actually adding carbon dioxide in the atmosphere. So, what happens? Carbon dioxide, because it is a greenhouse gas, it will absorb more of the radiation, and once it absorb more of the radiation, so the outgoing radiation will be less, because there has to be a balance between incoming and outgoing radiation. So, because you are not allowing more outgoing radiation, the radiation will increase in the atmosphere, and that is what the greenhouse gases do actually. So, this means if you keep on increasing greenhouse gases, it will keep on trapping more of outgoing thermal IR radiation, and this will lead to a further increase in the atmospheric temperature. So, this is also very important that we should not increase carbon dioxide concentration too much. So, this is what we discussed today, and just I give one last thing in this one before we conclude to this session, because it is very important again here. I talked about these equations, control what controls climate on the planet. So, if you see this one, and I said that solar energy or solar constant is almost constant, not varying too much. This picture shows about 1980 to 2005, and different labels. WM 2000, World Meteorological Organization, has given the data about 2003. So, you can see here that the global change in the on the y axis you have actually irradiance change. So, irradiance change is just about how much, actually 0.1% on either side. So, whether either it can be plus 0.1% or minus 0.1%. So, actually if I just take this one plus 0.1% or so, so S0 is 1370. So, this means actually just if I take it 0.1%, it will be 0.137 0.1%, you can 1 watts per meter square, or so 1.3 or 4 watts per meter square. So, it is not actually varying too much, but and this is also very important that it varies with the 11-year cycle. So, in a 11-year cycle, the S0 variability is about 0.08 or 0.1% in this one. Okay. Then then another very important, the second important thing was albedo. So, albedo, actually what is albedo, or reflectivity we also call it. So, albedo is a measure of how much light is reflected back from the Earth's surface. So, the greater the albedo, the more light is reflected. So, this means there will be the cooler atmosphere planet. So, if you see in the slides, it is shown that you have a low albedo about 10%, and here this means, and about out of 100%, 90% radiation is absorbed. So, you have a very high temperature, but if you have a high albedo and incoming radiation is scattered or reflected back, you will have a lower temperature. And these are the average albedo for the Earth, about 30%, but it varies seasonally. During winter months it increases, and during summer month it decreases, because summer times lots of plants leave their leaves actually. So, photosynthesis is stopped. Okay. So, this is also very important. Then in the summer it is further lower, and autumn further increases. So, change in albedo through land use can also affect the climate. and these are some values of albedo for different systems. Fresh snow, the albedo is about 80 to 95%, old snow is little bit lower 50 to 60%, sand beach on the desert is about 20 to 30%, grass is actually reflecting, but very less 25 to 30%, dry soil is also reflecting, but only 15 to 25%, and forest is least reflecting, which is about 5 to 10%. So, we discussed this one, we discussed this one, yeah. So, I think we discussed enhanced greenhouse gases effects as well, or what are the importance. So, I think I will stop here again. So, thank you for joining me for this lecture, and if you have any further question, you can just drop me email, or you can just write down text message or email. Email is better actually, and you can look more of details of mine on the either on the social media channels like Twitter, Facebook, LinkedIn or Google Scholar. So, thank you so much. Thank you.